Okay. Ooh, that clipped. That clipped again. I need to turn down the volume on the mic. Okay, that looks a little bit better. Okay, so my name is Scott Grizzard. This is Discrete Math. I teach at the University of South Florida. This is Discrete Math class, remote, not online. I've been told by the dean. It's remote teaching, not online teaching. Anyway, so today is the 22nd of April, and we are going to be talking today about finite state automata and regular expressions. All right. There was a quick question. There was a question in chat. The question is test 3. I think they mean test 4. Is test 4 the next one going to be shorter since there are fewer topics? No. So remember that every test is cumulative. So, I mean, you guys did well enough on test 3 that you probably shouldn't worry about that. So there will be material from the previous tests. I'm going to tell you about it in advance, probably tomorrow, maybe Friday, when I finally finish the thing. But yes, so test 4 is cumulative, just like test 3 was cumulative, just like test 2 was cumulative, just like test 1 was cumulative. So, well, I probably will end up being shorter anyway, but it's not designed to be shorter, if that answers your question. And then there's a final exam that is also cumulative, but on the final exam, I get to pick more topics. So on test 4, I'm not going to be including RSA. I won't be including Diffie-Hellman. Those are highlights of the course. They're wonderful highlights of the course, but they're not they're not the foundational number theory stuff that has to be, that you really, really, really need to understand in order to do the later stuff in cybersecurity. The logic stuff you need and all that stuff. Now, the final exam is longer, and it will include Diffie-Hellman and RSA. Okay? So I hope that answers your question. Are there any others? Okay. So as you can see, I think I mentioned the microphone last time. I got it working, obviously, because now it's dual channeling. It's in both ears. It turns out you have to set it as a mono stream in OBS, and it works. It's all interesting. I've also upgraded the system again, purchasing the Elgato Uber Elgato card. Nice. This was the last streamer card apparently in Tampa. So that should help with the black screen stuff. Because the black screen, even if it starts doing black screen on the tablet, it won't do it on the stream side for Elgato. It was pricey. It was as I said, the last HDMI capture card in Tampa, and I bought it. I had to call around, a bunch of different stores to find out someone who had anything, and they had that one. Probably it was on the shelf because nobody wanted to pay that much money. I was desperate, and I did apply for a grant, so hopefully I'll get reimbursed for all this stuff or some of this stuff. I won't get reimbursed for all of it, but we'll see. But I'm not spending money feeding graders, so yeah. Stimulus check. Well, no, that went to but yeah. So the I'm not feeding graders right now because usually I feed the graders when they're doing stuff. So I don't have to do that right now because they are grading remotely. They're still grading, and I'm not feeding them. Also, another issue that was asked was the issue about the fact that the grades lag you get a score, but the Canvas grade doesn't update. That's because Canvas doesn't allow extra credit on tests unless you kind of work around it. So what I had to do was I had to take your grade, and then I had to manually enter it as a new column. It is what it is. It's the way Canvas works. Are there any questions? So other questions? Okay. So you can go ahead and type questions in there. Let's go ahead and go to the quiz. Okay. So the quiz, as usual, graded out of 10 points. It's an 11-point quiz. Let's talk about this one. So this function moves toward 0 from the previous quiz. We can bring it up if you so desire. So we had this function moves towards 0 from the previous quiz. And the question was, if I have a, if the function check halt. Now remember what the function check halt did. It checked to see whether or not I halted. So it returned true if the function would halt, given the data, and false otherwise. So this is an even number. It's a very large even number, but it's an even number. And eventually this thing will move 2 down, and it's even. And because it will move 2 down, it will eventually terminate. However, this one is odd, so it will get stuck in that 1, -1, -1, 1, 1, 1, -1 type cycle thing, and it is false. And then the other one, it's 0, is an even number. It doesn't do any loops at all, so it just does, it terminates. How do we feel 1 to 5 about this particular, how do we feel 1 to 5 about this question? Okay, so people feel pretty good about that. Very nice. Okay, so yeah. All right, this next one, consider this chunk of code. So again, I gave you at the end, I gave you at the end last time, I gave you an assignment to go and to go forth and read about regular expressions. And I'm told that you all have seen this before. So, let's see, poll. Seen reg X before. So, just asking, have you seen this before? Yes or no? Before this class? Okay. So they're lying to me. I was told that you're getting it in Java class. Apparently you're not. So the poll is thumbs up, thumbs down. Yes, you hate it. Well, I'm going to explain to you why regular expressions are nice and why we care about them today. Okay? So this preg match here, let me bring it up on a, nicer thing here. And it's still gray. So my question was, would each of these match? So the first one doesn't match because this thing requires ending in A. This one matches because I've got A, and then I've got A's and B's in between, and then I've got another A. And that's also why this one matches. This one can't match because of the C. So if I pull up my, not there you are. It might help if I'm not in the peer leading file. So if I pull up, this file was reg text php.exe, and I get the answers: false, 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 true, right? So this one evaluates false because I didn't end in A. This one here validates as true. This one validates as true, and this one validates as false because I've got a C in there. So how do we feel about that one, 1 to 5? Okay. And if you have any questions about it, please post them in chat. I will be happy to discuss them. But I can't go any questions about that because obviously it would take forever while you're typing chat questions. Okay. Now, there's an issue that maybe you're getting an 8 out of 10 instead of it saying 10 out of 10 and waiting for that 1 point. I don't know. Canvas is weird. It could be the fact that I've got a bug. It could be the fact that the key is keyed in incorrectly for one of them. I will look. Okay. I've still got to fix the other one too. I still don't know what's wrong with that one either. All right. Are there any other questions? Okay. All right. Well, let's talk about these regular expressions thingies. So, finite state automaton regular expression. Let's talk about it. And the big name here is Stephen Kleene. We're going to talk about Kleene's theorem, but we're not going to prove it. And the whole point of this. So last time, there's a note. Technical correction from last time. I got yelled at by someone on the internet, and the person on the internet is correct. What we talked about last time was the fact that that the halting problem is not decidable. Okay, well, the book didn't go really big into that, so I didn't go really into that. So that's why the word is different. I said computable, not decidable, and someone was saying, well, technically it is computable, it's just not decidable. Okay, fine, whatever. Decidable just means you always get a true or false answer. The book didn't go much into decidable. I tried to go into decidable at the very beginning of the course, and then, when we went online, I said, I'll do what the book does, sort of. So that's why I didn't say decidable. I said computable or whatever. So last time I said problems. I talked about problems that are not decidable and the fact that these things exist. Okay? So, if you're on the internet yelling at me, that's fine. Go ahead. Mea culpa, I admit it. Okay. And I also spelled clean wrong right here. Okay, so today we're going to talk about finite state automata and regular expressions. Your book introduces regular expressions first in 12.1 and then talks about finite state automata in 12.2. I am going to talk about finite state automata. Well, I went and asked you to look up regular expressions on your own, and I'm going to talk about finite state automata. And the easiest way to talk about it is with an example. Okay, so have you all seen this before? Just out of curiosity, who has seen finite automata done before? Thumbs up, thumbs down. Okay, so most of the people haven't seen it yet. So the idea behind a finite state automata is I have a machine that's, rather limited, and it follows a couple rules. It has states, and it has transitions. And then it has an input. Okay. And the syncing is very slow. And I don't know why I move when I do that, but I do. It's probably because there's something wrong with the way I've set it up. So I've got states, I've got transitions, and I've got input. Now, an input is just a string of characters. Technically from some alphabet, I don't care. Right now, it's just a string of characters. Okay? Transitions are labeled arrows. And states are basically nodes. And there are three types of nodes. Okay? And a node can be more than one type at the same time. That's important to know. Okay? So a state can be initial, and terminal, and, just a state. So let's look at some input. Let's do an example. And the only way to do this is with examples. Otherwise, there's technical definitions. They are in your book. The finite state automata is the three tuple of this, this, and this. One of the tuples is shut up. Don't care. Let's just do the intuitive thing, because that's what we actually care about. Okay. So let's say I've got some initial thing, and this is the indicator for my initial. Start here. And I've got a state. And this is my initial state. And then I've got another state over here that's circled. And this is a terminal state. And I can have only one initial state. Okay? But I can have multiple terminal states. And then I can have multiple states that are just hanging out. Okay? Is everyone kind of on board with this idea of a state? It just hangs out. Now, let's do a particular one. Now, when I do a label, let's say I read the letter A. Okay? If when this thing reads the letter A, if this thing reads the letter A, it moves to the next state. Otherwise, it gets an error. Okay? So if I have here the letter A, where's the letter B? So what I'm going to do is I'm going to say, okay, if I'm followed by another A, I go to this state, and that's a terminal state. And if I get a letter B, I'm going to go to this state. So if I get a letter A or a letter B, I'm going to go to this state here, which is not a terminal state. Now, if I'm at this state and I get a letter A, I go to the terminal state. Oops, I'm sorry. This should be a B. So if I go from here to here, if I get a B, I go here. If I get another B, I go back. Here's A, and here's A. And then B will send me back to one of these states. And I actually don't care which it is, so I'll just send him back here. This right here is the terminal. These other ones don't have names. So now I'm going to read my word. So I have a word. So let's say I have the word AA. Okay? And let's show what happens here. So I started with the word, so I start here. Now I had the word A. So now I went to here. Now I had another A, so now I went from here to here, and this word was recognized. I arrive and stop. How do we feel about that? 1 to 5. This idea that what I did was I read off my tape AA. Okay. Let's do another example. Let's do the word ABA. No. Okay, well, I thought I copied it. There we go. Same machine. Let's do this word here. So what path am I going to follow for ABA? Let's see. My first letter is A, so I'm going to follow this path here. And now I'm here. How do we feel about that, 1 to 5? Okay. Well, now I've got a B. So my next letter is going to take me from here to here. You know what? Let me change the color of the highlighter. So this one was A. This one is B. How do we feel about that? And then for my last letter is A again. I'm here. And so I'm going to go down the A path to here. Okay. And then from the start, I arrive and stop at a terminal state. So my machine recognizes that word. Okay. So there's a question in chat. If I don't stop at a terminal state, it won't recognize the word. And the answer is yes. Where does... Oh, this machine, yes. So A would not be recognized. I don't have a state. For this machine here, I don't have something going out. So let me do that. Okay. So let me change the thing a little bit and allow it to recognize another A. So as you can see here, when I stopped at A, I didn't have a word there. So yes, you are correct, and I didn't mean for that to be. I wanted it to recognize that word as well. Well, let's do another one. Let's do that word you were talking about there, Brendan. Oops, sorry. I didn't. I'm sorry. I mentioned your name in Twitch, and I'm not supposed to. Sorry about that. So, your word was, yeah. So let's do the word AAB. So again, my initial state is A. Now my next jump here is B, is another A. So for this one, I need to use orange. So for this one, I'm going to go down the A path. And now I'm going to go down the B path. Okay. And I end okay. How do we feel about that? This word does not match that. That word would not be recognized by that automata. Okay. Well, let's look at the sort of words that this thing recognizes. Would this recognize any word that had a C in it? I should mention that. So let's say the word is C A B. Okay. So same automata here. Okay. But I started with C. I can't go anywhere. I get stuck. So my word does not match. Okay. Same thing. If I had the word AAC, here I would wind up at a terminal state. But then would not be able to handle the C. So my word does not match. And some books, your book, I didn't see it in here. That doesn't mean it's not in here. When they do them, they have something called the junk state. Your word doesn't have it. And your word has its state. Your book, by the way, has its states labeled. I didn't label them. You can. But I can have something called the junk state. And so the junk state takes anything else. And then the junk state has a loop for by here that says anything. Let me change the color of the word terminal here. Okay. So, and it's a non-terminal state, right? The junk is non-terminal. So if I feel uncomfortable with this idea of not being able to recognize C, I can put in a junk state, but I can exclude the junk state just because, it always does the same thing. And since it always does, who cares? We could just exclude it. How do you feel about that 1 to 5? That I have this thing called the junk state that just takes everything else. And because it just takes everything else and then you can never escape it, it just does nothing. So if you don't like this idea of getting stuck, you can add into your finite automata something called a junk state and just have everything go to it. Okay. So if I wanted to write this particular machine, okay, let's go back to my machine. What types of words does this recognize? Anyone want to hazard a guess? Well, let's look at our quiz. Yeah. But what types of words does it recognize? That's the question. Well, let's look at our code from the quiz. Yeah. So I've got a string. Let's see. Okay. So on the quiz, these were our words. Our test words were AAB, AB, AB, ABA, AAAA. I'm sorry, 4 A's, and AB, ABC, ABA. So for AAB, I go A, B, and I wind up in a non-terminal state. Okay? Everyone on board with that? 1 to 5, how do we feel about that? That path. I started here and I went A, B. And then I've got this word here, AB, AB, ABA. So I start here and I go A, B, A, B, A, B, A. And I end up at a terminal state. So I've been recognized. Okay. Well, how about this one? A, 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 A. All right. Well, here's A, 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 A. Terminal. I match. A, B, A, B, C, A, B, A, B, A, B, C, So, I'm in the junk state. I got junk. The point is that any string that matched this regular expression. Anything that started with an A, ended with an A, and had either any number of A and B's in the middle would match. How do we feel about that? 1 to 5. Now, we start to see the logic behind regular expressions. The reason why these are important is because it's efficient. It's very efficient. Very, very efficient to compute these things. It is very efficient to compute whether or not something matches one of these strings. Okay. Let's do another example. Let's do another example. All right. What we're going to do here is we're going to have a start. We're going to go from here. We're going to let this be anything. Oh, no. Anything's going to go here. So we're going to have a loop that takes anything but A. And this thing here is going to be A. And then we've got another one that has A again. And then we have our terminal state. And our terminal state says anything. Okay. All right. So now I've got this thing going on here. I've got anything but A, anything terminal. Okay. And then I've got a junk state here. So what does this machine do? What words does it accept? Okay, that is my question. What does this machine accept? What has to be? Will this machine accept C, A, D, E? Will that machine accept that word? What do we think? All right, accept or fail. Thumbs up, thumbs down. I don't know. Okay. And the answer is yes, it will. All right. I loop around anything, 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 anything. Okay. Now, what about the word C A D E? Yeah, right? Because now it went from anything, 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 A, junk. All right. Well, so with this accept, this won't accept anything with two A's in the middle, right? What will this thing accept? Verbally describe what this thing would accept. The reject is because I wound up going down C, then I wound up at C. I'm sorry, then I took an A, and then I took a C, right? And because I took a C, I wound up at here reject. But it's not anything with two A's back to back, because this has anything with two A's. Well, it's actually a little bit more than that, right? It will accept any word that has two A's before any other A. So if I wanted to do a regular expression for this, how would I do it? Let's write it. There we go. If I wanted to do a regular expression for it, how would I do it? Any word that has two A's before any other A. So here at the beginning, what would I need? Okay, let's see. Looks to me like this would be A, B. Let's just do lowercase characters. So A, B, no B, B through Z. Right? Any number of characters B through Z. Okay? Not A through Z, because I want to reject words that have a single A and then go to another character. So if I have A there alone, it's not going to work. Right? I need to reject things that have A's. But I'm okay with words that start with A, right? A is fine. So what I want is this asterisk. I want to say any B through Z, any number of those, including 0, right? I'm okay with a 0 there. And then I'm going to say I want two A's. And then after the two A's, I don't care what you throw at me. I will get at that one in a little bit. Okay, so my words were C C A A D E. Now let's leave this one in here. Let's add these two words. All right. Let's run that piece of code. Now, two A's and a B match. A, B, oh, nope, B there. This got rejected right then. Right, I went A, junk. A. Well, that's fine. A, and then anything. A, B, C, A. Nope, A, B. Got rejected. A, B. C, C, A, D, E. C, C, A, D, E. C, A, D, E. C, A, junk. How do we feel about that one? 1 to 5. Okay. Okay. So, question. So, how would I write a machine that would accept any word with two A's in the middle? I want to write a machine that would accept that last word. Okay. Question still stands. How could I write such a machine? Okay, that would be a regular expression, and it's not quite that. It's a good thought, though. Well, I need some state, but what do I do if I get there? You're correct in one sense, right? So the idea is an arrow going back from junk to another state. Um, well, that's kind of the idea, except why don't I just skip the junk altogether? Why don't I just skip junk? Right? Why don't I just skip the junk? Why don't I do the exact same thing I did here? How do you do that? You're supposed to be able. Oh, forget it. I got a mouse. But instead of having this junk state, what if I took it out and did this? Now what would happen? Well, now when I did this word, CAADE, I'd go from start, right? I have a C, okay, an A, but then I have a C. Up, go back. And then I have AA, and then I make it to there. So this allows for single A's first, but then I skip back to the beginning if I wound up with a single A and waited for a double A. So this accepts any word with a double A. Okay. And the regular expression for that would look like this. It would look like that. Now, and let's test it out. There it is. Right, so this had two A's, this had two A's, this did not have two A's, that had two A's, and that had two A's. Right? So this says right here anything, AA, anything. How do we feel about that? 1 to 5. They're kind of fun, aren't they? They're kind of cool. Okay. Okay, so if you think of regular expressions, okay, the point of this is if you could think of regular expressions as machines, and then they actually make sense, right? The regular expression, the syntax you read, um, the whole point is that the syntax you read in the programming manuals is annoying and boring. But if you think of these things as finite automata with arrows and rules, they actually sort of make sense now. Okay? And the reason this connection is called Kleine's theorem. Kleene's theorem. Anything. Okay, so a word, a pattern, a regular expression. Every regular expression corresponds to a finite automata. There we go. Every regular expression corresponds to a deterministic finite finite which word did I end up using? Oops, I'm on the wrong one. There we go. And I want to use the same. I'm trying to use the exact same expression in the book, so I don't want to use state deterministic. I want to say finite state automata. And every finite and vice versa. In other words, the words yeah, that's enough. I don't want to get into languages and all that. Who cares? We don't need to sit here and study context-free languages. It's not something that's going to be practical for us. Okay, so that's Klein's theorem. Every regular expression corresponds to a finite state automata, and every finite state automata corresponds to a regular expression. Okay. How do we feel about this 1 to 5? That's what the whole point of this is. Right? Every finite state automata is a regular expression, and every regular expression is a finite automata. Proof in the book if you're interested. Okay. Well, automata is the plural. Automaton is the single. It should be an A. There we go. No N there. That's an M. Automaton. All right. And that was the point. Okay. But there are things that I can't do with regular expressions. Now, it should be said that, as I'm saying this, it should be said that there are extended regular expressions. There are things that computers support, that programming languages to support, that they call regular expressions that aren't. Regular expression is actually a technical term. So things you can't do with regular expressions. Now, Michael had one before. He said, can I have one with prime numbers in the thing? So can I have the thing that says, can I have a regular expression that says the following? Okay? And the answer is no. Why intuitively? I'm not going to go through proof, but why is the answer no? Why is this not possible? Yes, so it's not possible because there are infinite prime numbers, but there are an infinite number of even numbers as well. And I can do one with infinity. So there's something more to this, right? I can do something like this. This part right here, I can do this. And I can also do something like this. So I can do two ways. I can also do even A's by doing odd A, by doing any number of A's. Let me remember how to do that. Let me see. On regular expression syntax for PHP. Sorry, because there's several different syntaxes, and I want to make sure I'm using the right one. I think it's parentheses. Yes. Okay, so it's this. I can do this. And I don't want a star. I want I think it's a plus. Regular expression, match. No, I don't want greediness. Okay, so what I wanted was any number of A's in the middle. So even A's. So I would do AA as a group. And then it depends. Am I okay with 0 being an even number? If I am, then I would use this. If I'm not, I'd use a question mark and then one of these. And then I want to reject everything else. So this right here would give me so if I wanted this, this would be B through Z, B through Z, and this would give me star, this would give me star, like that. So this would be even A's in a row, but no strings of odd A's. And then I'd probably do a that, and then in there, and I start here. This is even A's and odd A's first. You can make one that's more difficult. Okay. All right. Okay. So the TA ruined the punchline for me. That's perfectly good. Go for it. So I can't do something where P is a prime. The other thing I can't do is this. I can't do something like this. Okay, I can't have matches that look like this. And the same reason, I'd have to have an infinite number of states. And the proof of this, there's something called the pumping lemma, which lets you prove these things. I'll just write that as an aside. I'm not going to ask you that on a test, but if you care. The way you prove these things is something called the pumping lemma. But again, that's more mathy than we want. The big picture here is that there exist things that I can't do with regular expressions. Okay? Now, I need to put a little star here. Some languages, some programming languages have features they call regular expressions. So you have to watch out. There's terminology here, and you see this all the time. I mean, you've already seen it already. Some computer languages say, oh, we have this feature. Our regular expressions do more than regular expressions, right? And you're outside regular expressions at that point. Yes, there are computer programs that do things that are that do. Let me see. There's a technical word for it. I'll pull it back up here. Um, Unbounded back references and stuff. So with unbounded references, you can do this with you can't do this with regular expressions. But you can with something called a unbounded backfill, back references. However, back references are not efficient. So you can get into trouble with back references and things that aren't regular expressions. Okay? If that makes sense to you. Um, and so and different languages support different extended features, but some of these things are NP complete. So you can get into trouble. The nice thing about real regular expressions is that they're extremely efficient. Okay, and I want to make that I want to make that clear. The really nice thing. This is kind of the punchline of the whole thing, right? The really nice thing about regular expressions, truly regular expressions, true regular expressions is that they are extremely efficient. Okay, the matching for a regular expression is like the computer can do it like that. Okay, you match for some of these other extended things, and it can take the computer a century or two. But you match for a regular expression, and it's just like boom. So 1 to 5, how do we feel about that? Oops. How do I do this? I do 5 pull. How do we feel about that? The whole point is that these things are really, 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 really efficient, and I can use them in my programming, and they're not going to cause trouble. I can do preg matches, or whatever, and they make my life happy. They're easy to compute for the computer, and et cetera, et cetera, et cetera. Okay. All right. So today, what we talked about was finite state automata and regular expression. So we talked about what a finite state automata was. We didn't technically define it, but what we did, because that involves tuples and it's boring, but we didn't define alphabets or languages technically. The book does that. I just said okay, fine, and we unlabeled our vertices because we didn't care. But so we didn't do that, but we did talk about the notation. The terminal state is the double zero. I've got a little arrow with a start, and then I just label my things. So we talked about that. We talked about what a finite state automata was. We talked about what a regular expression was and the relationship between regular expressions and finite state automata. They're the same thing by Kleine's theorem. And then we did examples of things that you can't do. But again, there's this note that some languages support things that aren't really regular expressions, but have additional features. But those features can be inefficient, especially compared with regular expressions. And the whole point, and you will get your fill of regular expressions in your career, is that these things are really, really efficient and they correspond to finite automata, so you can make them fun. Okay. Are there any more questions? Okay. Next time, I want to talk about P versus NP, but of course, it's the one right before the lecture. I may come back, depending on the homework. I'll post a homework for tomorrow, and I will post a quiz. Depending on how the homework goes, I may talk about regular expressions again. If I don't talk about regular expressions again, I'll move on to P versus NP, which is actually related to this thing in chat that says, is RSA secure for emails? So it depends on whether or not it depends on how the homework goes, whether or not I just move on to P versus NP, which is really cool, do a little edutainment, or if I come back to regular expressions and we play with it some more. Are there any other questions? Okay, because I actually want you to get regular expressions a little bit. P versus NP is important and cool, but it's not as important to your career as regular expressions, which are boring. They can be cool because you do finite state automata. Okay, maybe I'll talk about non-deterministic automata next time. Okay, that's it for me. Thank you.